No, ma'am.
Hello, can you all hear me now?
Yes.
Yes.
I was on mute. Wow. I'm doing well. Okay, so when I'm talking about a difference operator, what will this be? How should I write my difference operator of xt? Anyone?
xt minus 1.
Right, it will be xt minus 1. So I'll have xt minus 1 here. And remember, now I can rewrite this xt minus 1 as minus of bxt, right? And again, I can rewrite this whole term as 1 minus b xt. And remember the previous condition that we wrote, that our difference operator is nothing but just 1 minus b. So this is how we get that difference operator is just 1 minus b. So it performs the same operation that 1 minus b would do on xt. Okay, so now let us try to see what happens if we have square xt. What will it be? Delta xt minus 1. And again, if I were to expand these terms, I will get xt minus 1 here, and then minus of xt minus 1 minus xt minus 2, which will be nothing but xt minus 2 bxt plus b square xt, right? And again, now I can just rewrite this, because this is just 1 minus 2b plus b square, as 1 minus b the whole square xt, right? So what I can deduce from here is that if I square my difference operator, I get it as almost approximately equal to 1 minus b square, because it again performs the same operation. So you can say that basically this is not the actual proof, but you see what's the pattern here, right? So by induction, you can say that in general, my difference operator, if raised to n, will be equal to 1 minus the backward shift operator raised to n. This is a very, very, very important relationship that will come in handy while we are dealing with ARIMA processes. This is really important. Does this make sense?
Yes, ma'am.
Okay, so Also, so whenever we have a inverted triangle in mathematics, it is known as nabla, and it's written as Nabla. So maybe instead of saying difference operator the whole time, I can call it nabla, and that is actually it is a symbol to measure some divergence and all the sort of stuff, but we don't have to worry about that. So let us now see what happens if I have a random walk. So can someone tell me what is the formula for a simple random walk? I can write it as xt being equal to xt minus 1 plus et, right? You guys know, right, what is a random walk?
Yes, ma'am.
So let's say if I say that my xt can take values only 1 or minus 1, then you will know that if I, let's say, have some timeline and I'm looking at time period 5, and if my x5 is some 9, then I know that my at time 6, x5 can take values either 8 or 10, and then for the next values, it can either take 11 or 9 again, and again here you will have 9 or 7, and all those will continue, right? So this is my random walk, and tell me, is this random walk a stationary process? What do you guys think? Is this random walk a stationary process? Anyone? So what kind of a model is this? Is this a AR or MA or ARMA, or what kind of a model do you think this random walk is? Anyone? So it
AR?
just looks like AR, right? It just looks like a AR1, because what we have here is only dependency till t minus 1. So it will be AR1 model. Perfect. And now if I were to check whether this model is stationary or not, what I can do is I can just write this as xt minus 1 equals to et, and then I will have xt here in bracket 1 minus b equal to et. And now I have to figure out the roots of this characteristic equation. For that, I equate this. So instead of b, I don't write b, but I use some proxy, which might be z equal to 0. So I know that my z is equal to 1, which is clearly not greater than 1. Therefore, as z is not greater than 1, the random walk is not stationary. Is this clear? But now let us look at its difference. So what if I write my nabla xt as xt minus 1, right? So if I see, and if I look at my nabla xt and compare this with the random walk that I have, this was just equal to et, right? So if I'm looking at the process, which is this, I can clearly see that this is a stationary process because it is nothing but just a white noise process, which is always a stationary process, right? So what we did was we started off with some process which is not stationary, and then we took a difference. So we took a difference and we ended up with a process which is a stationary process. So now we assume that for most of the process of our interest, it will be possible, if they are not stationary, to convert them into a stationary process by differencing. So here you had to difference it only once to get to a process which is indeed a stationary process. So let us say if you just define this nabla xt as something yt. So now you have another process where yt is just equal to et, right? And now this yt process is indeed a stationary process. But remember, what we are concerned with is not yt, but xt. So there will be something that you can always do once you get to know the actual model for this stationary process, to convert it, to inverse transform it again into the actual model that you were concerned with. And let us just try to do an example of that sort of now. So maybe I can write this here. So let us say we have a data set xn and we have calculated its first difference, and after calculating its first difference we got some model. So now I know that this is what I'm looking at. So the difference is, so this nabla xn is my one random variable, and this is equal to 0.5 nabla times xn minus 1 plus en. So what I did was, I had a series xt which is not stationary, but then I took its difference and I figured out that okay, this process is indeed a stationary process. Then I applied my empirical methods, which we will study in next chapter, of how to figure out these coefficients in these, all of these terms. So I got this model as the final model for my answer. And so remember, this is the model. This is not the original model, right? This is model for the first differences. And now I have to figure out what will be the model for my original series xn. What do you guys think I can do? Is there anything that I can do? Absolutely right. Maybe I can try to expand this. So once I get that my nabla xn follows this model, what I can do is I can write my this xn as xn minus 1 equal to 0.5, and I have nabla xn minus 1. So this will be xn minus 1 minus xn minus 2 plus en. And now I can just rearrange this for me to have 1.5 xn minus 1 and then minus 0.5 xn minus 2 plus en, right? So remember, the model for my first differences was an AR1 model, but now here, if you look at xn, it depends not only on xn minus 1, but also on xn minus 2. So this is a AR2 model, not a AR1 model. And now if you try to figure out the stationarity for this model, you will see that this is clearly not stationary. So what you will have to do, you will have to just take this on the left hand side and then figure out its characteristic equation and then take the roots, and you will get to know that this model is indeed not a stationary model. But we knew that the first differences of this model is a stationary model. So when I talk about xn, it will follow ARIMA. So first we have P, and if you see there is minus 1 and minus 2 here, so there is dependency for the two lagged. And now comes the important part. The number of times you have put nabla there, that will be the value for d that you have here. So the d will be equal to 1. And for MA, we don't have any of the lagged processes of E. So we only have 0 here. So if I were to write what model my XN here follows, it will be ARIMA 2, 1, 0. So remember this D here that I have is 1. So when I'm talking about the ARIMA model, I have, so the full form of ARIMA model would be autoregressive integrated moving average processes. And the word that say integrated just corresponds to the fact that you have to add up these terms here afterwards to convert the stationary process that you got into the model that you require for the original series. And that is about ARIMA. So let us try to do some more sums about ARIMA model. So again, the way I can write my ARIMA model, I can also use my ARIMA model to write normal AR models and MA models. So let's say if I have my ARIMA P, 0, 0, this will be just a AR model, right? And if I have my ARIMA 0, 0, Q, then that would just be my MAQ model. Or if I have ARIMA P, 0, Q, that would just be my ARIMA model with the parameters P and Q. Does this make sense?
Yes.
Okay. So now we will see what is it that we can do. So maybe let us just directly try a sum. Okay, good. So I have a nice sum. What we can do is, let us say we are given some model. So whenever you have ARMA model, MA or AR model, you can directly see and say, right, that this is my AR, MA or ARMA model. Once it satisfies, the stationarity and invertibility conditions. So now let us see that I have a process which is something like this. And we are asked to classify this process. Would anyone want to guess what kind of a process this is? So remember the lags of X that we have are up until 4, and for MA we don't have -1 but we have -2. So if I ask you guys to classify this process for me, what would you say?
ARIMA.
Yeah, I couldn't hear you.
ARIMA process.
ARMA process with what parameters?
4 and 2.
4 and 2. Okay, that is actually a very good guess. But let me tell you, that is not what this model is. So let us see what happens. First, we will have to check for even it to be a well-defined ARMA model. We need this to be a stationary model. So I'll check my stationarity first. So what I'll do is I'll rearrange all of this X's on the other side and I'll keep my ET on the RHS. So what I can do is I can take my 2 here, 2xt minus 7xt minus 1 plus 9xt minus 2 minus 5xt minus 3 plus xt minus 4, and that will just be equal to et minus 2. Now again I can use my backwards operator to rewrite these terms. So if I have xt here, what will I have here? It will start with 2 minus 7b plus 9b squared minus 5b cubed plus b raised to 4, right? So now what I have here on both of these sides is some characteristic polynomial for my MA model and for my AR model that I have. But now remember one thing, what I have to do is figure out the roots of this characteristic equation, but it is raised to 4. So instead of directly, trying to solve this using whatever techniques which we clearly don't know how to, what we try is whenever we are given such kind of a model and we don't have the calculators which would directly solve these values of b for you, what you can do is you can try and substitute the easier values first, and that will most likely give you the zeros. So let us try substituting 1 here first. So what do I get? 2 minus 7 plus 9 minus 5 plus 1. Will that be 0? So if I substitute 1 there for my b, will I get the answer as 0? I will, right?
Can I ask something?
Yeah, sure.
So here, why haven't you taken 2b to the power 4 minus 7b to the power cube?
2b to the power 4.
Like, remember
Oh, no.
how in one of those questions you
Yeah.
increase those subscript values by 4?
Yeah, so remember when I was solving for that question, what I had was a formula already in my table booklet to guide me through the process. So I
Yeah.
had a formula from the booklet which was for ax n plus 2, n plus 1 and n, where it
Yeah.
was decreasing in value, right?
Yes.
So just to make it easier, because we know that k would be the number which I have is the most higher one, then k minus 1 and then k minus 2. So just to make this a bit easier, what I did was I converted all of them into pluses. So I have k plus 2 here, k plus 1 here and k here. So that I get a similar equation to the one that I have the general solution for here.
Okay.
Yeah, and remember here we are looking at the rows. So here we were looking at the rows. And this type of thing can be done whenever you want to figure out this, or you want to figure out a general function for this, because in that case you will have to use the formula which is there in the book. So yeah, but here whenever you take the characteristic equation, you have to remember that you don't have to indulge into all those sort of stuff, because you have a backwards operator, right? So
Yes.
if you convert all of this again into pluses, if you can write this as xt plus 4, then you wouldn't be able to use b. I mean, you would still be able to use b, but it would still give you the same answer with just some different xt here, right?
Correct. Okay, I get it.
Yeah. So I hope that clears that was a good question. So yeah, let us move forward with what we have here. So let us say if I substitute 1, I get a 0. But for this case, I do get a 0, and this wouldn't be the case always. So if you do not get the answer 0 by substituting 1 in the case of B, try substituting minus 1, or then try substituting 2 or minus 2. But remember, in this in this chapter time series process, it will most likely be the case that the answer will be 1. Why? We will get to know in a bit. So if you divide this polynomial with 1 minus b, what will you get? Can someone divide this for me?
But if we know that the root is also, it is not stationary, so why do we need to know more roots?
Okay, so yeah, that is actually a very good question. So now we know that the first root of this characteristic equation is 1, and we know that this model is not stationary, right? But let us try to see what happens next. Let us try to see how many times do we have to differentiate, or how many times do we have to write this whole polynomial in different terms till the time where we get something which will have roots which are less than 1. Sorry, which are greater than 1 absolute value. So let us try to do that, and I'll tell you guys in a bit why and how we can convert this model, which is clearly not a stationary model, into a stationary model. So that was a very good observation. I know that the root is equal to 1. Therefore, my model is not initially stationary. So now I want you guys to divide this with this and tell me what should I get here as my quotient. Did anyone divide this?
It is 2 minus 5b plus
2
4b
minus,
square, 2 minus 5b plus 4b square minus b
yeah,
cube.
perfect. So this is correct. And now see, can you find the roots of this polynomial? Try to see if it works with 1 or if it works with minus 1. So I'll have minus 5, minus 1, minus 6, and 4 plus 2, 6, right? So 1 will work here. So again, I will divide this equation with 1 minus b. So I'll get some terms, and here I will have 1 minus b squared xt, which is equal to this. Now I want you guys to divide this again with 1 minus b. And tell me what do you get as the answer. Do you guys have the answer? Shouldn't take this much of time to just, divide and figure out the quotient.
Two plus 3b plus b square.
It is 2 plus 3b plus b square. Would you want to check the Plus and minuses. Is it 2 plus 3b or is it 2 minus 3b?
minus 3.
Minus, right? So what we have here is 2 minus 3b plus b square. Again, now figure out if you can find the roots of this. So let's try 1 again. We have 2 minus 3 plus 1, 0, right? So again we have root as 1, and again this model is still not stationary. But again we can take out as common 1 minus b. So now I have q here. Give me the quotient that will come there. I'll just have 2 minus b here, right? So if I were to say now, what I can do is, what happens, I can write my 1 minus b as nebula, and what I will have here is nebula cube. So what I can write this as 2 minus b nebula cube xt is equal to 1 minus b square et. So what you do is, now you always try to see, are there any common factors between this and this which you can cancel off. So now here I can see that I have 2 minus b nebula cube xt here, and I have something like 1 minus b square. So this is nothing but a square minus b square type formula, and I can write this as 1 plus b times 1 minus b et, and my 1 minus b is nothing but just 1 nebula. So I can cancel this here, and I can cancel this here and make it 2. So now the model that I have with me is, I can rewrite it as 2 minus b nebula square xt being equal to 1 plus b et.
How can we cancel the operators since one is applied on xt and the other is applied on et?
Yeah, one is applied on xt and the other is applied on et, but there's still, you can actually cancel this. So even if it is applied on xt and here it's applied on et, you can still cancel these operators. That's the beauty of these operators. It wouldn't change the relationship that you have with the variables. And that is the magic that you have here in this time series. So if I were to classify this model now, what I will do is, I will ignore this delta, I will ignore this nebula's power, and I will only look at the other remaining things that I have here and here. So I have to write my classification for this model now. So I know that it wasn't stationary in the first place, but now I have made it a stationary model because the root of this equation is only 2, which is in absolute terms greater than 1. So now this model is a stationary model, right? So what I will have here is, so now I have ARIMA, and here I can see that there is only b term here. So 1 instead of p, I will only have 1. And while writing what my value for d will be, always look at the thing which is in power to the nebula here. So I have 2 here. So I'll write 2 here, and I will write here 1 again. So the order of AR is 1, the order of MA is 1, and we had to integrate. So remember, this is not actually the number of times you have to integrate the process, because if you look at here, what we did was once, twice, and thrice, right? We did it 1 time, we did it 2nd time, and we did it the 3rd time. And still we don't have 3 here because there was one common term which got cancelled. So now you only have 2 here. So the number of times you in effect will have to, you will have to integrate it is 2 times. So this is what the classification as answer will be for xt process here for this process here. Does this ring a bell? So maybe, so I know this is a bit weird when I ask you to cancel this and that, but this can be done, because that is just, the beauty of the operator that we're looking at. And now I have classified this using one method, but I'm going to show you another method again for the same sum that I have to solve using something else. So that we haven't yet had a look at any time. So what I have here is 2xt minus 7xt minus 1 plus 9xt minus 2 and so on. So now what I intend to do is, maybe I can take these common. I can try to do, so just bear with me for now. I have 2xt here. So I know to take it as common, I will just take minus 2xt minus 1 out of these 7xt minus 1s that I have. So remember, I have minus 7xt minus 1 and I want to rewrite this whole expression in terms of nabla, which if applied on xt gives me xt minus 1. So I want to rewrite all of my expression on the left hand side in terms of this nabla xt or its powers. So let us see what I can do. So I have 2xt here and so for me to take common as xt minus 1 and then 2 will just come out. So I took out minus 2xt minus 1 here and then I'm left with minus 5xt minus 1, right? So this would still sum up to 7xt minus 1 minus 7xt minus 1. Okay, so now because I have minus of 5xt minus 1, if I want to take a nabla here, what will I have? I will have minus 5 as common. So I should have xt minus 1 plus 5 xt minus 2. Again to take this as common. And then I'm left with 4 of xt minus 2's. Good. So now I will be taking 4 as common. So I should only have 4 of xt minus 3 here. So I will write minus 4 xt minus 3. But I had minus 5 to begin with. So minus 5 minus 4 is nothing but minus 1. So I will have minus 1 xt minus 3 left. And I can just rewrite this as it is. And this will be equal to et minus 2. Does this make sense? So what I have done is, if you add this and that, you will get this term right here. If you add this xt minus 2, you will get this term. And if you add this xt minus 3s, you will get this term here. So this is in essence just rewriting the actual model that I had at hand in terms of the convenient way so that I can use nabla and my difference operator to rewrite it. So now if I were to write this equation again, I can just write it as 2 nabla xt. So this will be xt minus 1. So taken into account. Now I will write minus 5 nabla xt minus 1, right? And then plus 4 nabla xt minus 2. And then there is just minus nabla xt minus 3. Again being equal to et minus 2. Maybe I can use my nabla here as well. What do you guys think? Can I use my nabla there as well?
Yes.
Yes, I can, right? but we'll have a look at that a bit later. So let us now try to figure out, is there something else that I can do with this now? So I have 2 nabla xt and nabla xt minus 1 here. So again, I will try to see if I can have a difference here. So what I can have is, I know that my nabla square xt is nothing but nabla xt minus nabla xt minus 1. And you use this fact now to say that I can rewrite my this expression using nabla square xt. And to do that, you again perform the same kind of operations on this equation now. So what you will get is 2 nabla xt, and now you want minus of nabla xt minus 1. So you just take 2 of those again. And now you have minus 3 left. So here you have 4 of these. So you only take 3 of this for it to be, common. And now you're left with 1 of those. So you write 1 nabla xt minus 2. And what you will have is this as it is. Does this make sense? So now I can again take this 2 common, and I will have nabla xt minus nabla xt minus 1, which I can write as nabla square xt minus 3 nabla square xt minus 1 plus nabla square x t minus 2. And this is equal to et minus . Does this make sense?
Yes.
Now again, you try to do the same thing on this operation right here. So you remember the fact that if I were to write my nabla cube xt, it will be nothing but nabla square xt minus nabla square xt minus 1. And you try to perform the same operations on this again. So what you get is 2 nabla square xt is what you have. And what you want to do is you want to take 2 out of this. So you take 2 nabla square xt minus 1, and you're left with 1. So minus 1 times nabla square xt minus 1, and you have nabla square xt minus 2 equal to et minus 2, right? So now I can again rewrite this as 2 nabla cube xt, right, which will account for both of these. And now I'm left with this, which will just be minus of nabla cube xt minus 1, and that is equal to et minus 2, right? So
Yes.
again, now you can see we have started the same process. We started with the same process, and now we're just looking at another method of figuring out the parameters of the ARIMA model for this process. So if you stop right here, what you will notice is the degree to which my nabla is there, the degree to my nabla is 3, right? So the D should be 3. And I'm looking at xt and xt minus 1. So my p should be 1. And here my q should be 2. But we already know that, this is not the answer. We know that the answer is something else. But is there something else that we can do here? So what I will do is, I'll write my nablas as 1 minus b, and I will have this in terms of backwards shift operator as well. So now what I will do is, I will write this as 1 minus b cube, and I will take that out as common. So what I will have is, so maybe just to start off with, I will write this as 2 minus b times nabla cube xt equal And I know that this will give me 1 minus b square et, right? And again, now I will substitute 2 minus b, 1 minus b cube xt equal to 1 minus b times 1 plus b et here. And you can cancel this and that for 2 there. So you get the same thing that you got in the previous case. And now you can conclude that this is ARIMA 1, 2, 1 model. So these are actually 2 different methods, but the easiest one is, of course, the previous one. And this second process takes so much of time. And remember, here you have to keep on, factoring this out until and unless you get the roots of this equation, which is left, to be greater than 1 in absolute terms. So you keep on doing that, and always in this C6 prospects, you will get 1 as the solution until and unless you get, some stationary here. So you will have those added in powers, and you will have something as 1 minus b square here, or something else which will again have 1 minus b as the common factor, and these might cancel, or this may not even cancel. So it doesn't matter. And that is how you have to keep into consideration. If you have any commonalities between these, you can cancel it out. Even though it is just an operator, it allows us to do all of these calculations, which just gives us the actual model that our process follows. And the second method was this. This is a bit tedious. I'm not particularly fan of this method, but I like how intuitive this method is. And that's just, you just have to know that, this method also exists. So now let us have a look at something else. So in your book, you guys are given a nice example. So what we just saw in an example, let me generalize it and write it down for you guys to, have some nice thing here. So let us say I'm looking at ARIMA process, and the way I can generalize my ARIMA process, so if I were to write my ARIMA process in terms of general, variables, I will have something like 1 minus alpha 1b up until alpha p b raised to p, and 1 minus b to the power d x minus mu equal to 1 plus beta 1b, and this will go on till beta q b raised to q e t. So that is how I get my p, I get my d, and I get my q for my ARIMA p, d, q model. So there are certain other examples which they have shown in the book, and I guess I will just leave you guys to go through that on your own. And now let us try to see what kind of a model is my random walk. So we started off with a random walk model, which was this here, right? So if I were to classify this model, how can I classify this model now? Anyone would like to try? So I have to differentiate once, and then I get something like this. So what will be my P, my Q, and my D in this case? Anyone?
Zero comma 1 0.
Exactly right. So I don't have any of the lagged values for nebula xt here. No xt minus 1, nothing. And I don't have anything here as well. But I had to difference this series once to get to a stationary process. So I have 0 here, 1 there, and 0 here. So my random walk process is just a ARIMA 0, 1, 0 process. So in the next chapter, we are going to study something known as Box-Jenkins methodology, which will, allow us to classify these models practically. Let's say when we are given some data, how to make sure that, all of the properties that make a model as ARIMA PDQ model are being satisfied by our process. So stationarity, invertibility, and all the sort of stuff. So we'll have a look at that. And now let us move forward with another concept. So I think you all must have heard of Markov property.
Yes.
I'm sure you all have. So what does it say? Anyone?
The future values of a process do not depend on the past values and only on the current state.
Yeah. So is my random walk a Markov process? What happens in random walk? I have xt equal to xt minus 1 plus et, right? So I can clearly see that today's xt depends only on xt minus 1, right?
Yeah, it is.
Yeah, so this will be a Markov property. So when I'm talking about a Markov process, there is, so let me just write the heading first. So we're looking at Markov property. So in the previous chapters, where you guys must have studied about the Markov process and this property in particular, you guys were looking at discrete state spaces, right? Because there was some particular value that your x can take, right? Among the 1, 2, 3, 4 values. So what happens here in time series is, now because you have a continuous state space, so our xt can take values within a continuous state space. So you cannot just say that your xt will take some value. So let us say if I were to write my Markov property for discrete state space. What I would write is that the probability that my x today will take some particular value, which is small a, given that I know the values it has taken prior to t. So I'm just assigning some random values, and that will be a bunch of xs equal to xs. Right? So I know that this is all the history that is being given to me, and this is what I have to figure out, given that I know all of this history. And if I say that this xt is a Markov process, then I know that the dependency or the future development of this process can only be predicted from its latest state that I know. So this will just be equal to the chance that my xt takes value a, given that my xs takes values x. Oh, it should just be s. Just for the consistency of notation, this will just be x, right? And that happens in the case of discrete state space. So here we have to take into consideration that all of this ss are less than this. and which is less than t, right? And we have these values. So this is the time that I'm looking at, and my state space is comprising of x1, x2, x and a, right? So I have a comma x1, x2 up until x here, and this is my state space. So let us denote it as s, and this is my time. But now we know that whenever we are looking at a time series, the state space is not discrete. It can be continuous. So in time series aspect, what we will have is a continuous state space. So do you guys think that the definition of a Markov property should change if I'm looking at a continuous state space? Or can it remain the same? What do you guys think?
It must remain the same, except that the value will be in some limits.
And what do you mean by, the value will not be in some limit?
Can you please repeat the question once?
So my question is that if I'm looking at the continuous state space, can I write this for time series?
So instead of A, it will be xt belongs to A, where capital A, where A will be a subset of S.
Where A will be a subset of S, right? So what we will do is, we cannot write xt equal to A, right? Because when I'm looking at a continuous state space, the probability that my xt takes one particular value out of all those infinite values will be almost zero, right? Always. So what you do is, you take an interval. So instead of this equal to A, what you do is, you take an interval A, and you say that, and you calculate the probability that your xt will belong to this particular interval A given all of this. And that will just be equal to the probability that xt belongs to this interval A given that your xs is x. And again here, you know that all of this s1 is less than s2, so and so till s, which is again less than t, and x1, x2, x, all of this are in S. And this A right here is also a subset in S. So I can maybe write my A here as well. So is that clear to everyone? So if you were to, use the actual properties and say that my A will be some subset of S. But you don't have to worry about, those set notations. You just have to know the fact that the prediction of xt at time today will depend only on what happened yesterday, not anything which has happened prior to that. So when I say this sentence, what I actually mean is that if I know that my xs has taken the value x, I don't need this information to determine what value my xt will take. And that is what I'm looking at, right? Because you can easily see that even if I write a random walk process. So let's say I write a random walk process, which is something like this, plus et. So what do you guys think? Here xt just depends on xt minus 1, right? But what if I say that I can write my xt minus 1 as xt minus 2 plus et minus 1 plus et. So now I can again make an argument that my xt is depending on xt minus 2, right? Not only xt minus 1. So this is not a Markov process. but that would be a false argument. So you have to be aware about these tricks as well and only take into consideration the information. So given that you have some information about xt minus 1, so now you know what the value for xt minus 1 is. Can you determine the value of xt without using the information in xt minus 2? And that you can do, right? So you do not need this xt minus 2. And that is why that random walk still satisfies the properties of being a Markov process. Is that clear to everyone?
Yes, ma'am.
So if I were to classify my random walk, it is just a AR1 process, right? So I know that my AR1 process, given any AR1 process, I will have that process to be a Markov process. So now let us have a look at what happens if we are looking at a multivariate time series. So remember, up until now, we were looking at only one of these random variables, x. So what happens if you have multiple random variables? So the whole models that we have yet studied are for univariate time series. Whenever you are looking at one particular model, one particular random variable. So now let us see what happens if I have a number of variables. So in essence, I would be looking at multivariate time series models. So let me just write that. Okay, so when I'm talking about a multivariate time series, I will again have my xt. So remember the xt that I used to have previously, I will still have that xt, but it won't be a number now, you know, it won't be only one component. It will have multiple components, and let us say that we are looking at a m component time series. So I can write that my xt is a vector here, and so sometimes you can also denote it by this arrow, but I'm just going to, resort to denote it by a bar underneath. So I'm writing my xt as xt1, comma, xt2 up until xtm. So when I'm saying that I'm looking at a multivariate time series, remember the components that I have at time t are m number of components. So I'm looking at m number of time series at time period t each. And that is what I denote as xt. So now if I were to ask you, what should this process xt satisfy for there to be stationarity? So for stationarity, I know that I want my mu t to be expectation of xt always. And remember again, this mu here is a random vector, and this xt again here is the random vector. So this mu t will be, expectation of xt, which will, so sometimes you write it like this, or sometimes you can write, a transpose here. So that when you write expectation of xt, you will get something like expectation of xt1, expectation of xt2, so on till expectation of xtm. And that will be your mu t here. Does this make sense? And now the next thing that you will have a look at is the covariance. So remember, now that you have m number of components, how many covariances will you have to look at? Anyone? How many covariances will I have? M times m minus 1, right? Again, also taking into consideration, also not taking into consideration the variances. So what I can write is For my covariance now, I will have a m by m matrix. So this will be a m by m matrix where you will have, let's say, xt1, xt2, so on till xtm. And again here you will have xt1, xt2, so on till xtm. And you will have some values here. Right? So whenever I'm talking about the variance, so here it will just be variance of xt1. Here it will be covariance of xt2 and xt1, which will be the same here as well. So these kind of matrices, where if you ignore the diagonals, they are symmetric, right? So covariance matrix, remember this covariance matrix will always be symmetric because you know that covariance of xt2 comma xt1 is equal to the covariance of xt1 comma xt2. So these kind of matrices will always be symmetric, and all you have to worry about next is that it should also be independent of t for it to be a stationary process. So these have to be independent of t as well. And remember, now I can, if I'm writing my this covariance, I will write covariance of xt comma xt plus k. So again, this xt here will be some vector and this xt plus k here will be some vector. And then you will have to, figure out this covariances, and you will have a matrix which you denote as sigma. And this is the dispersion. And here you have mu t, which you denote as mu. And again, this is a vector and this is a matrix. So you have to know that this is a m by m matrix, not exactly a vector. Does this make some sense? Do you guys see some issues with what I have just written? So I'm saying that I'm looking at a covariance between xt and xt plus k. So what do you guys think the subscript here should be? Will it be m times m? No, it will depend on k, right? So when I'm looking at the covariance of xt comma xt plus k, I will have xt on one side and I will have xt plus k on the other side. So if my t plus k, if my k is a negative number, then I will have less of these values, right? So, and if my k is a higher number, then again I will only have t of these values, because then there won't be any correlation between those to carry out. So this here is going to just depend on t. I mean, I'll show that to you guys in the next chapter again using some nice or maybe today itself you can have a look at that. So now if I have to write my multivariate time series models, what I use is something known as vector autoregressions. So remember the model that we looked at was AR model, right? And now I have a vector. So this V is just for vector. So now the models that I will have will be var, not only AR but var. And again, they will have some order, which is P. So now if I have to write my multivariate autoregressive process, I can write it as something like this. So I'll have my xt here Remember, this is a matrix, and that will be my mu, which is also a matrix. Because if I have a matrix here, it can only be, a sum of other matrices. So I'll have plus summation j going from 1 to p, and I'll have aj, which is again a matrix, and x t minus j minus mu, which is all of these are matrices, plus pt. But now we have to make sure that these multiplications hold true and that the dimensions of all of hello. Can you all hear me? Hello.
Your voice isn't clear.
Yeah. So where my ET is something which is a m-dimensional white noise process. Okay. And what will be my AJs here? So my AJ here is some m by m matrix. And these are just, to figure out the coefficients of xt minus 1, xt minus p. And those will be matrix m times m. So you know that if you multiply these matrices, you get something which is a m by 1 matrix again. So I hope you guys know that, let's say if I have A here and if I have B here, so my A here is m by m matrix, and instead of, so let us just write X here. So my X here has to be a m by 1 matrix for me to carry out this multiplication and have something which is m by 1. So this and that should be equal. So the number of, so can someone tell me what is this m and what is this 1 here? Is m my number of rows and 1 my number of columns here, right? So the number of columns of A should be equal to the number of rows of X here. So I know that my X is a m by 1 process. So when I wrote previously a transpose here, you don't have to do that, Just consider X as a m by 1 process. So, oh, sorry. So you have to do that. Yeah. Because you have m number of rows and there is only one column. So this will be a m by 1 dimensional vector, right? And thus you also get here m by 1 dimensional vectors. So, yeah. And now again, so we see that the ETs are white noise process, right? Which are normal 0, some sigma. So if I were to write the variance for this E now, it will be nothing but the dispersion matrix. And what do I mean by dispersion matrix? So it is this sigma here. And that is how you denote the dispersion matrix, which is just, the covariance matrix rather, to say it nicely, for ET. And it will have nice rows and columns. So yeah, that's how you write a vector autoregressive process. And again, now we will see what conditions these processes have to satisfy for it to be a stationary process. So let me take an example. So I have two processes, xt and yt here. Maybe we can start off with something else. So let me write it as, let's say I give you two processes, xt and yt. So xt here is 0.3 xt minus 1 plus 0.5 yt minus 1 plus et, and this is for x. And yt I can write as 0.2 xt minus 1 So I have these two processes, and as you can clearly see, the main motive to go with, solving for these models using a multivariate time series model is that my xt not only depends on xt minus 1, but also on yt minus 1, right? So the xt that I have, the one variable that I have, not only depends on its own lagged values, but it also depends on other values as well. So what I have here is xt is some function of xt minus 1 and yt minus 1, and yt is dependent on xt minus 1 as well as yt minus 1. So if I have to write this in terms of vectors, how can I write this? So let me show it to you how to write this. So I have xt and yt here, and I know that these depend on xt minus 1 and yt minus 1 respectively, and simultaneously as well. So what I do is I create a vector of xt and yt, and I will have some things here, and I write xt minus 1 here and yt minus 1 there, plus etx and ety. So I know that to get xt, I have to multiply the terms which will be here with xt minus 1 and the term which will be here with yt minus 1 and then plus etx, right? So the coefficient of xt minus 1 for xt is 0.3 and the coefficient of yt minus 1 for xt is 0.5. Similarly, for yt, I'll have 0.2 here and 0.2 there, right? So if I were to compare this model now, so you see, right, I have a vector here, I have some matrix here, and again I have some vector here, and again some vector here. So if I were to compare this, I can clearly see that my sum vector here is equal to, so because here j is only 1, you don't have the sum, you only have this one of these. So aj here is this matrix right here, and this is some vector, and then this is the vector which share the same dimensions as the one that you look for. Does this make sense? So
Yes,
yeah, so this is a two-dimensional process now. We started off with looking at m-dimensional process, but here we only have xt and yt, right? So let us see that my wt comprises of xt and yt. So my wt is a 2D process. So now I can write this model as wt being equal to, so again I'm just naming this matrix as A. So that will be A right there, and you will have wt minus 1. So if my wt is xt comma yt, my wt minus 1 will be xt minus 1 and yt minus 1, right? So I can rewrite this as wt equal to awt minus 1 plus etw. So I'm using this right here. Write this, write this, and write this. And this whole matrix that I have here is the A that I'm looking at. Does this make sense?
yeah.
Good. So the only thing that I forgot to do is write a transpose here. So this can be, important things that you might miss out on as well. So now I have to figure out a way to check for the stationarity of this process here. But I know that wt and wt minus 1 are vectors. So what you can do is, instead of, so previously what we used to do is, we used to check the stationarity by seeing the roots that we get for the characteristic equation or the polynomial, right? But now what you will do is, you will have to figure out the eigenvalues. And if those eigenvalues are less than 1 in absolute terms, you will get that the process is stationary. But what will you figure out the eigenvalues of? So let us say I again rearrange these things. So what I can write is Wt minus A, Wt minus 1 equal to Et W. All right. And even if you don't do all of this, actually, you are just, so remember when you are looking at vector cases, you should never do something like that. Just take this coefficient of Wt minus 1 that you have here. So what you do is, you take the value A and you figure out its eigenvalues. So the way to figure out eigenvalues is something like this. You take the determinant of A minus lambda I and equate it to 0, where A is the same matrix that you have and I is the identity matrix. So if I have I2, it will be 1, 1, 0, 0. So what I will do is, I will have A minus lambda I. So for my A, I have something like 0 0.3, 0 0.5, 0 0.2, 0 0.2 minus lambda times I, which will just be lambda lambda 0, 0. And now this should be equal to 0. So actually this shouldn't be 0. The determinant of these should be 0, right? So now if I were to write it again, I will just have something like 0 0.3 minus lambda, 0 0.2, 0 0.5 and 0 0.2 minus lambda's determinant to be 0. And I am hoping everyone knows how to figure out the determinants. It will just be this multiplied by this minus this for a 2 by 2 matrix. So what I have here is 0 0.3 minus lambda times 0 0.2 minus lambda minus 0 0.5 times 0 0.2, and that should be 0. And now to figure out the value of these lambdas here, you will have to solve this quadratic equation. So if you write this, you will get something like lambda squared minus 0 0.5 lambda. And now you can use, plus or minus b square formula to figure out the values of this lambda. So you will get lambda 1 as 0 0.57 and you will get lambda 2 as minus 0 0.07. And now to see if my model is a stationary model, what I want is these lambdas to be less than 1, which they are. So if my mod of lambda is less than 1, it implies that the model is a stationary model. And where this lambda eigenvalues. Does this make sense to you guys? Were you guys able to follow what I did?
Yes.
Also, I don't know if you guys already know, but there is a very beautiful theory of why taking a determinant of this equation gives you the eigenvalues, and what do you actually understand when I'm talking about the eigenvalues. And I think if you all have encountered a video of Grant Sanderson, so he owns this YouTube math channel called 3 Blue 1 Brown on YouTube, which is quite famous. So he has, very nicely explained why do you have this sort of expression to figure out the eigenvalues and what it is exactly, meaning when you are talking about the eigenvectors and its eigenvalues. So I think so it has something to do with, you know, some vector and then you are looking at another vector which is just similar in similar direction, but I think I'm going to save that explanation for now because we clearly don't have much time, and maybe I can put up a link of that video, you know, in the Google Classroom for you guys to watch. And I think it's really cool. And I hope you all have heard of 3 Blue 1 Brown. If not, I think you should definitely go and check his channel out. So yeah, so this is how you figure out if a process is stationary. And now if I have to see if my process is indeed an invertible process or not, what do you guys think I need to know if I want to see if my process is invertible? So remember the time I was talking about invertibility for a MA process? Maybe we can go and have a look at that. I think it was this. Yeah. So what we have here is we are looking at invertibility. So when we were talking about a process which is supposed to be an invertible process, we know that if we can write this ET in terms of XTs, then I can say that my process is an invertible process, because for this inverse to exist, this process has to be an invertible process. And if it exists, then I know that I can rewrite my ET, which is the noise term, in terms of the x's here, xt minus 1, xt minus 2, and all the sort of stuff, right? So now if I were to figure out a way to say that, so the thing that we looked at here was stationarity. Now let us have a look at its invertibility. So when I'm saying that I want my process to be invertible, I know that I should be able to rewrite my VAR's error process in terms of its excess, right? So what I had was that my WT is equal to AWT minus 1 plus ETW. So this is the error process that I have. And if I just rearrange this, what I get is ETW equal to WT minus A, WT minus 1. So you see that I can easily invert this, right? And that is why a VAR process of any order. So here we have a VAR 1, here is invertible. And in general also, any VAR process with any order P will always be invertible, because you can always write the ETWs in terms of WTs and its lagged variables. So you know that once you have WT and WT minus 1, it has XT minus 1 and YT minus 1 and XT and YT. So you can always write the error term of X, which is ETX, in terms of XT and XT minus 1. So I'm just rearranging this to go on that side. And if you take the upper variables, you get that you can write ETX using XT minus 1, XT and YT minus 1, right? So you can easily say that this is an invertible process. Now the next thing that we have to talk about is indeterministic. So whether my VAR process here is indeterministic. Do you guys remember what do I mean when I say indeterministic? So what do I mean when I talk about a deterministic process? If I know something has happened today, then I can know for sure what exactly is the value that my random variable will take tomorrow. But as long as we have these error terms here, we can never know for sure, because this is the random fluctuation that we have within our model, which if were not present, then we would say that my WT is equal to AWT minus 1. And if I give you the value of WT minus 1, let's say if you know the value of the variables at T minus 1, then you can easily know the value of WT as well, and so on, if you know the value of A, right? But what happens is you have this random fluctuation which plays a part. So as long as you have these ETs, the process will be not deterministic. So if any process has error term, the process is not deterministic. And the last property that we'll have a look at is Markov. So can I say that my random variable WT here is a Markov process?
Yes.
Right, because WT is fully determined if I know the value of WT minus 1. I do not need to know any of the previous values to know what the value will be for WT, right? So my VAR1 is a Markov process. Good. So now if I look at any other process, can I say that it will be a Markov process? So when I say any other process, let me just try to write it down. What time is it? Okay, we still have nice time. Okay, so if I'm writing some, let's say some another process, which is a AR2 process. Let us say I have a AR2 process, and what I have here for AR2 is xt minus 1, I'll have xt minus 2 and some error term, right? So if I have to write this in terms of a matrix form, how can I write this? So I have to write this in terms of a matrix form. So I have xt minus 1, and I have xt minus 2. So what I will do is, I will write another equation of xt minus 1, which will just be 1 times xt minus 1 plus 0 times xt minus 2. So this process is nothing but, just xt minus 1. I have just used some manipulation here and rewrite it as some equation. So now I will use this first and second expression to write this AR2 in terms of a VAR1 model. And why would I even want to write it as a VAR1 model? Because I know that if I have my AR processes, so if I let's say have my AR2 process, will that be a stationary process? Anyone? Sorry, will that be a Markov process?
No.
No, right? Because my xt depends on xt minus 2 as well. So I know that if I have a VR model with P as 1, it will always be a Markov process. So maybe if I can rewrite my AR2 model as VR1 model, I can allow it to follow the Markov property, right? So how is it that I can rewrite this now? So what I will do is I will just write xt here and xt minus 1 here. So this is one vector that I have, and then so I will just write this as WT. So you want WT minus 1 to be here, right? So it will just be xt minus 1, And for xt minus 1, it will be xt minus 2 plus some error terms, right? So I know that for xt, I have an error term which is et, but for xt minus 1, there is no error term. So I can just write it as 0. And now again, alpha 1, the coefficient of this is alpha 2, the coefficient of xt minus 1 is 1, and the coefficient of xt minus 2 is 0. So this is how you can convert a AR2 process into a VAR1 process. So this is all about converting an AR process of P order into a VAR1. So now let us say I give you a AR3 model. Can you guys try to write a VAR1 model for that? Okay, so try to write a VAR1 model. What will be the first step? Anyone?
Writing the equations for xt minus 1 and xt minus 2.
So yeah, you can write equations for xt minus 1 and xt minus 2. But to know in what terms you should write the equations for xt minus 1 and xt minus 2, you have to know what are this and that. So if I'm having a AR3 model, what I will have is 3 components for my time series here. So I will write xt, I will write xt minus 1, and I will write xt minus 2 here. And then I know that there will be some 3 by 3 matrix here, for which I have to figure out what the coefficients will be. And there has to be the lagged values of this there. So I'll have xt minus 1, xt minus 2, and xt minus 3, plus some another vector. So now you know that I have to write xt minus 1, and xt minus 2 using xt minus 1, xt minus 2, and xt minus 3 only. So now you figure out the equations for xt minus 1 using this, and now you figure out the equations for xt minus 2 using this. In the same way, I figured out, and I just convoluted an expression for xt minus 1 here. Right, you just put 0 to all the coefficients which you do not care about. So now if you are looking for xt, right, in terms of these, the coefficient of xt minus 1 is just alpha 1. For xt minus 2, it is alpha 2, and here it is alpha 3. And here you will get 1, 0, 0, and here you will get xt minus 2. So 1 there and 0 elsewhere. And you know that there won't be any error terms here. So 0, 0. But there is one error term that I have for xt. So I'll have et there. So this is again a VAR model, right? This is my WT, and that will just be my A, and this will be my WT minus 1, and that will be my error term for W. So this is how you can convert any ARP process into a VAR model of order 1, which is always a Markov process. Does this make sense?
Yes.
For everyone, did you understand this?
Yes.
Yes, ma'am.
Okay, so you can take some time to assimilate what all we did today. Let me just have a look. Did I miss something? Yeah, so they have some examples and some questions for this Markov property. And I think if you just go through them, on your own, I think that those are pretty easy. No, I think, wait, we do have 5 minutes. So maybe we can, summarize this whole concept that we have just studied. So what I have is, in general, if I'm looking at an ARP process, and if my P is 1, it satisfies the Markov property, otherwise not. But I know that I can always rewrite any ARP process in terms of a vector valued process, which will be a Markov process. So in general, if you have to write this, how you can rewrite this as is, so